right, so thank you guys for joining us for the final session of this afternoon. So our first speaker in this session is Emma Vo, who you can see here on our screen. Emma has already departed Pasadena because she recently started graduate school at the University of Central Florida. But she very graciously agreed to come remotely and join us to tell us about her project this summer. So Emma did her undergrad at UC Riverside, and she's been working this summer with Drew. And today she'll tell us about her project with Drew, the detection of the Kaiser effect in the intergalactic medium surrounding protoclusters. Go ahead whenever you're ready.
Hi everyone, like Gwen said, I'm Emma, and I really wish I could be there in person with you all, but still I thank you for coming here to listen to me talk. So let's get started. First, why does all of this matter, right? It's kind of the overarching question in any field of science. But really, mapping protoclusters using Lyman-Alpha is really revolutionary to understanding the galaxy clusters that we see today. So protoclusters are the overdensities of galaxies at a certain redshift that eventually become the galaxy clusters that we see today. And so by looking at protoclusters and understanding them, we can more better understand the galaxy clusters that we see today. And it kind of just makes it a lot easier to understand the evolution of our universe as a whole. And so the observation of the Kaiser effect acts as extra proof and evidence towards protoclusters that Drew found with his team are not artifacts in the data and are actually there. I'll get a bit more into that later on, but you'll see that the Kaiser effect is actually really useful into proving the existence of protoclusters. And so really my work this summer has been working on plotting the flux of galaxies measured through Lyman-Alpha so we can look for those redshift space distortions and look for those absorption patterns. But really all of that only made sense if you work in astrophysics and astronomy and you only work with this kind of content. So if only some of that made sense or none of it at all, don't worry, I'm going to go into some background that'll really help with understanding what I did this summer. So firstly, what is Lyman-Alpha? So when it comes to the hydrogen atom excitation, when hydrogen atoms are neutral and they take in energy from photons, they use that energy to move their electrons around. And so there's a few different series that describe the types of electron movement going on depending on where they start. So more specifically, we'll be talking about the Lyman series, which is where the electrons start on the very ground state of the atom. But more specifically, we'll be talking about Lyman-Alpha, which is the first jump in that series where the electron goes from the ground state of the neutral atom to the first excitation level. And so that's what we'll be focusing on for most of this project. And so when we have a galaxy or a quasar like I have on the left here, it's going to be releasing a lot of photons in a whole bunch of different directions. But there's going to be us, the observer, and we have photons coming at us at a certain line of sight. But between us and that galaxy or quasar is the intergalactic medium, which is just kind of the space between a bunch of galaxies. And within that medium, there's a bunch of clouds of neutral hydrogen. And when those photons are going to hit those clouds, it's going to energize them, right? It's going to give energy to those electrons, and they're going to jump around in those levels. So when the photons are moving, we measure an energy flow or a flux. And when they hit those clouds of neutral hydrogen, we see a dip in the flux because they got absorbed. And so we don't see that energy from the photons anymore because they got absorbed by the neutral hydrogen, right? So that brings us to the Lyman-Alpha Forest. So when we look at the whole spectrum of flux from a distant galaxy, there's this initial section there that has a bunch of these little lines. Really cute name for it, Lyman-Alpha Forest, because it looks like a bunch of little trees. But really, it's a bunch of those absorption lines that I showed you in that last slide. It's a bunch of those dips from photons exciting neutral hydrogen. So that's really what we're going to be looking at here, is the Lyman-Alpha Forest. And so that's going to bring us to this really new, cool technique called tomography. And tomography is used to make maps of large-scale structures using Lyman-Alpha flux. So Drew and his team in 2020 was able to do this, which makes these beautiful maps you can see here on the right. But really what they're doing is they're looking at the amount of flux and being able to tell where there's large scale structures in the universe. So by looking where there's the least amount of flux, that means that there's going to be more absorption in those areas, which means that there is more of a density there. And so by using that kind of methodology, they can tell where different large scale structures are. More specifically, what Drew did was his survey called LATTICE, which stands for Lyman-Alpha Tomography IMAX survey. And that is the image directly I have here on the right. But he used it more specifically to find protoclusters. So you can use it to map out any other large scale structures, but he used it specifically for protoclusters. And so we actually looked at background galaxies to map out these protoclusters. So able to tracing the density in the foreground using background galaxies is a really cool technique. So really when you have a bunch of background galaxies that are releasing photons towards us and giving us that flux, you can see something in the foreground because it's blocking those areas. So by using background galaxies and measuring the flux from those, we're able to actually map out the density of protoclusters. So we're not actually looking at the galaxy population of the protoclusters, we're actually looking at the density of flux around them, which is actually really interesting and really cool because sometimes with protoclusters, it's hard to look at all the galaxies that are within it. So using background galaxies is really useful, so we don't have to actually look at the protoclusters themselves. We can still find them and map them out. So again, Drew was able to do this with his team in 2020, and that's the beautiful map you see on the right there. And Lattice is actually what we used all the data this summer from. So a bit more specifically to what I'm looking at is the redshift space distortions and kind of an intro into that. So because protoclusters are so large and so dense, there's a lot of mass. And when there's a lot of mass, there's a lot of gravitational attraction. So all the matter around these protoclusters ends up being pulled in towards the center of the protoclusters. And when we're looking at redshifts, redshifts are a measurement of both distance and velocity. And because it's based off velocities and movement, the redshift space actually gets distorted. So these peculiar velocities of the matter around protoclusters causes a distortion when we look at them in the redshift view. So compared to what would look like round in real space, actually ends up looking squished in redshift space because of the movement of that matter. And that's really what we're looking for. So the Kaiser effect is that squishing that we're looking for. And the image that I have here on the bottom is by Kim et al. In 2015. Kim did some studies involving the Kaiser effect, but using quasars instead of protoclusters, but still the same kind of, the same thing that we're looking for is the Kaiser effect. So as you can see on the left here, I have like the 3D real space image of what you would expect to see when looking at a quasar, something round and uniform. However, on the left, you can see the image of the Kaiser effect, where it actually ends up looking squished. So my whole goal of the project was to look for images that look similar to the one on the right and kind of find evidence of the Kaiser effect. So moving a bit more into my specific process, my measurements and their implications. So my first starting steps were loading in data from Lattice. So I just took in all the information from Lattice and I created plots of the Lyman-Alpha absorption around absorption peaks. So absorption peaks are the areas in the line of sight that have the most amount of absorption or the least amount of Lyman-Alpha flux. So as you can see, the bottom left here, I have just a general view of the flux from just a very certain galaxy. That's some of the first graphs that I made was looking at individual galaxies. And then I normalized the flux. As you can see, it kind of hovers around 1, which means like 100% of the flux is being sent towards us, which is what you would normally expect. But when you see the dips, that's the flux getting absorbed. So as you can see, I centered these graphs around the absorption peak. So the red box here shows the absorption peak that I actually centered the graphs around. And the one on the right is basically the same exact graph, just zoomed in a little bit and interpolated, just so I can look at it a bit more intensely and so I can see the more details with the absorption. So after looking at individual peaks of galaxies, I chose to look at all the galaxies around a bunch of absorption peaks within the Lattice data and average those all together. So the image that I have on the bottom left is going to be a graph of all of the data from Lattice averaged into 1. So as you can see, it's a really strong absorption peak because it's all the absorption peaks all averaged together. But the one thing about doing that is that it actually kind of takes away some of the nuances that you can see in terms of the absorption strength, because sometimes absorption peaks can have different amounts of strength. Which is what I ended up actually doing was splitting the absorption peaks from the data into different bins of strength. And as you can kind of notice here, the ones that have stronger amounts of strength actually correlate to more negative values. And the reason it does that is because the quantifying number of strength relates to the amount of flux. And like I mentioned earlier, the amount of flux is kind of negatively associated with the strength. So something that is more strong of an absorption peak means that there is less flux, which means that the strength factor would be more negative. So the entire Lattice spectrum goes from -infinity to -2. So the strongest bin I have here is going to be all the way on the left, which is the most strong one. It has -infinity to -3.8. As you can see, it goes pretty close to 0. It's a pretty strong absorption bin. The next one is -3.8 to -3. You can see a little bit of disparity in the bottom of the peak. You can see it's a bit less, but it still is a good amount of absorption. And then the next one I have, you can really see the difference where it's -3 to -2. You can really see that it's a lot weaker of a bin than compared to the rest of them. So then finally, I was able to actually find evidence of the Kaiser effect, which is what these images on the bottom here are. So I was able to plot all of that data in 2D to look at the absorption patterns. And we were able to detect the Kaiser effect as in the absorption peaks as a whole and also in those different strength bins. So on the left here, I have the full image, so you can really see the effect of the Kaiser effect there. The one thing though about lattice is when we get in the data from it, because protoclusters don't have a certain projection in the sky, they don't have a preferred orientation, we actually end up averaging the data. And so when I get in the data, I actually would get this as a half map. So I would only see about half of this round structure here. And so I just mirrored this image so you can really fully see the Kaiser effect. It just really helps visualize what we're looking for. And then on the right here, I have a few quarter images. So I have quarter images because I took those half images I got from Lattice and actually flipped them over and averaged them again to get them very average so you can really see the patterns. But as you can see them within all the strength bins. So the top left, I have all the data of Lattice, and then I have them going into the other bins of strength. And you can see on all scales, the X goes farther out than the Y does, which means you can really see that squishing effect, which is exactly what we wanted to see and really great. And it was super exciting when I was able to get these images. And so what does all of this mean and where do we go from here, right? So Drew in 2022 with his team found that only half or about half of the Lyman break galaxies were actually missing around the strongest strength bin of absorption peaks, which is kind of concerning because you would expect with the strongest strength bin to be a lot of galaxies. So when you see some of them missing, that's kind of concerning. So by looking at the Kaiser effect, I was able to provide actual additional evidence to Drew that these are true overdensities and true protoclusters, and they're not just artifacts in the data. So it is something that he truly found, but it is kind of weird how we're missing some of those galaxies, but it can help him by kind of giving him evidence like, hey, they are there, don't worry, just something happened where we can't see them. But so the Kaiser effect was really able to just provide some extra evidence. But Kim et al., who also did the study in 2015, like I said, was doing studies on the Kaiser effect with the quasars, actually predicted that the amount of squish is not sensitive to the mass, which is something that was kind of surprising to me. But so therefore, my observation of the Kaiser effect doesn't prove evidence towards the mass of the overdensities. It just proves evidence of their existence. So even though we're able to say, hey, they are there, I can't prove how massive they are, which we were hoping to be our next step was quantifying the amount of squish. But that would definitely be some future work. Drew and I found that it's actually a lot of work to quantify the amount of the Kaiser effect. So that would be able to be done with some mock Lyman-Alpha tomography surveys, and that would take a whole summer on its own. So that'd be some future effects with it. But yeah, I had a great summer and it was super exciting to find the Kaiser effect and help Drew out. Thank you all for listening to me and let me know if you have any questions.
Questions for Emma? Emma, just checking, can you hear me on this?
I can.
Okay, perfect. Questions for Emma?
Hi, Emma. This is Allison. I really enjoyed your talk. I was just wondering, in the plots you showed of the absorption peaks, it looked like some of them might have been double peaked or there was something going on there. Is that physical or is that just a matter of resolution or something?
That's definitely a matter of resolution. There is a lot of noise on these plots. So yeah, even though it looks like there are some like huge peaks over here, that's definitely just noise. But you can really tell the difference between an absorption peak and noise because you can see most of the distance between. You can really tell that this is a true dip and not just some noise. So yeah, these are quite noisy plots, but that's why I tried to do some things to kind of like zoom in and kind of focus more on the absorption peaks so I can look at them in more detail because they are quite noisy.
Other questions?
Hi, Emma. It's really nice work. I also thought, like you, that the amount of squish would be related to mass. I was surprised that it's not. So I wanted to ask you like what other causes could be. Like I know you said that you will look into that, but I guess what I'm asking now, which things you would plan to look at as other possible sources of the amount of squish.
Yeah, so I think everything that I looked into kind of pointed a bit more towards the radius of the density being a bit more influential in the amount of squishing that you see compared to the mass. But I didn't have as much time during the summer as I wish I did to be able to look more into that. I definitely do think that that's some of the things that some of the papers have been kind of suggesting, but there isn't a lot that kind of explains that. So that'd be my best guess from what I looked into, but I'll definitely have to look into it more.
All right, we should probably move on, but let's thank Emma again.
That's great.